So I'll like to welcome you who are attending, and not least, I want to welcome the presenter for today, José Sigut saavedra from University of La Laguna on the Canary Islands in Spain. And José, you are going to talk a little bit about the medical diagnosis using AI application on retinal images, as I understand. And this is a very interesting topic. AI is very hot, and all the kind of typical different application and use of AI is of great interest and importance. So please, Professor Sigut, the floor is yours, and those who are here are eager to hear and listen to what you are.
Okay, thank you. So I share the screen.
Yes, please.
Can you see it? It's okay?
Yes.
Okay. So hello, everyone. Hello, Gunnar, and thank you very much for organizing this STAR talks, and also for the invitation to give this specific talk about medical diagnosis using artificial intelligence and its application to retinal images. I have divided the presentation in two parts. In the first part, a general approach to the problem of applying artificial intelligence to the diagnosis of eye diseases will be provided. I will start by giving an overview of the medical problem at hand. Then I will introduce some concepts and terms related to this in this context, so that you can get familiar with this, more familiar with this field. And I will finish this first part by talking about some of the challenges you have to face also regarding this problem. In the second part, I will focus more on some examples of our research work on some of the topics we will have discussed in the first part of the presentation. Okay, so what problem do we want to solve? We will talk about eye conditions, eye diseases, and this is a substantial source of morbidity around the world. Worldwide, over 2.2 billion people have this sort of suffer from this sort of diseases, and the situation is even worse in low-income countries. This has also an important influence and impact on economic productivity, with an estimated productivity loss due to these diseases amounting to about 410 billion US dollar. There are, okay, I made a mistake. In the beginning, I said 2.2 billion, not 2.2. Let me just try to. Okay, now. Yeah, it's okay, because I had this, I could not see. I just minimized the something on the screen, and now it's okay. So I was saying that there are some different types of diseases, of eye diseases. Some of the most representative ones are uncorrected refractive errors, cataracts, age-related macular degeneration, glaucoma, and diabetic retinopathy. I will be talking in more detail about some of them later. And the point here is how AI can help in this problem. AI can be integrated into the ophthalmology workflow in different ways. Here I'm showing some usual tasks in the medical field where AI can be integrated. We have diagnosis. I think everybody knows what diagnosis means. Screening, maybe you're not so familiar with screening. Screening is more like trying to identify in a set of subjects, individuals, which individuals are likely to be suffering from the disease, so that they can be treated accordingly. Then we have monitoring. It just means monitoring the evolution of the disease, and prognosis is more about predicting the evolution of the disease in the future. Okay, so we can integrate AI in any of these tasks. But the way we integrate it can be also considered in two different ways to do it. It can be an assisted way, which means that, okay, the specialist can use AI as a tool, but the final decision, the important decisions will be taken by the human specialist, or they can be, we can be talking about a completely autonomous AI system, which at least ideally would be able even to take the final decision about the diagnosis, for example. As you can imagine, in a critical field like medicine, it's difficult to find a completely autonomous system in practice, because usually there's some sort of human intervention at some part of the process. On this slide, we have a nice picture extracted from the Lancet Global Health Journal very recently in 2023. They published a paper. Here you have the DOI of the paper if you want to have a look in more detail. And in this, as you see, what we have here is a timeline of the developments both in global eye health and also in the artificial intelligence related to this global eye health, okay? So it starts from the very beginning in the 1800s, but as you see, most of the milestones here are concentrated from 2010 approximately. What's the reason for that? If you see, in 2011, there's a very important milestone in the history of machine learning, because deep learning surpasses human performance in pattern recognition. That means that the era of deep learning started, so that any task in machine learning, in machine learning related to computer vision or natural language processing was the traditional techniques were replaced by deep learning techniques, because their performance was much better. So that's why it completely changed everything at that time. Another two dates I like to remark here are 2016 and 2018. You see here, deep learning model validated for diabetic retinopathy screening. And in 2018, very important also, the FDA approved the first deep learning autonomous model called IDX-DR. It's interesting to say that this is not only it's the first FDA approval, not only for medical diseases, but in general, in the medical field. So this is a very important event. And just as an anecdote, I'd like to say that I was in 2015 visiting a scholar in the University of Iowa, working with Professor Michael Abramov, who was the person who really developed this. So I was there at the time. I remember that this project, but I was not really involved in it. And just to finish with this slide, as you see, we have later than 2018, we have other systems which have also been approved by the FDA. And this is more or less how deep learning has progressed in the last years. Okay, now let's have a look at the type of images we will be dealing with mostly during this presentation. I'm talking about eye fundus images. Here you have an example. On the left of the slide is a normal left eye. On the right of the slide, we have a normal right eye. Well, there are here, this is actually an image of the retina, okay? So, and we have some structures here which are important, the vessels, the macula with the fovea approximately in the middle, and the optic nerve head, which is where the information acquired in the retina conveys and is transmitted to the brain, to the visual cortex to be processed there, okay? Okay, these images are actually very simple images. They are RGB images, which can be similar to the ones you can capture with your camera and your mobile phone. Actually, there exist some devices that can be put in your mobile phone so that you can take this type of images, but in practice, it's more usual to acquire them using this sort of medical device. The equipment you see here on the right is called a retinograph. And well, the patient just sits next to it, and through the pupil, As you see here, you take the picture of the retina, which is here, of the eye fundus. On this slide, we have an example of diabetic retinopathy. This is a very important disease, a very serious one. As you can imagine, because of its name, it has to do with diabetes. And on the left part of the slide, you can see a simulation of the effect of diabetic retinopathy on the vision. Okay, you see the strong loss of vision due to this disease. On the right of the slide, what we have is what is really happening at the level of the retina. As you see, there are some sort of spots, different types of spots, microaneurysms, hemorrhage, hard exudates, soft exudates, and these spots in the end will cause the loss of vision we see on the left. Since we are this talk is in the framework of STARS-U, I like to talk about, and STARS-U is about regional transition, regional transformation. So I like to mention a regional approach in the Canary Islands to this problem of diabetic retinopathy. I'm talking about Retisalut. Okay, it's important to say that in Canary Islands, we have a high prevalence of diabetes, actually the highest in Spain. And for that reason, a screening program called Retisalut has been working in the Canary Islands since 2007. Since that time, more than 800,000 images have been collected with the main objective of trying to early detect the diabetes in primary health care centers. That's the point here. We do that in the primary health care centers, and for that purpose, more than 45 retinographs have been distributed in different centers. We have nowadays currently an application called Luxia, which is a cloud-based screening tool, which has been developed by researchers in one of the hospitals in Tenerife. The hospital is called Hospital Nuestra Señora de la Candelaria, and this system has been trained with images from Retisalut and has shown a good performance. So this is an example of a successful approach to the problem here in the Canary Islands. Okay, and just to finish with this first part of the presentation, let me raise some clinical challenges about how to bridge the chasm between AI and clinical implementation. There are some of them, there are several, but I have included on this slide just two of them. Clinical validation. Okay, this is about the need for testing our systems, our AI systems on large standardized data sets which represent real-world settings so that they do not introduce algorithm biases. This has also related to ethical concerns because in 2021 a paper was published where it was said that the publicly available of ophthalmological data sets, which are usually taken to train these AI systems, only did not include featured subjects from 172 countries. So that means in practice that if you try to test your system trained on these publicly available data sets, you try to test it on images coming from these countries. For example, it could happen that you had overfitting. Overfitting is a very known problem in machine learning, and it has to do with the fact that the system is not able to classify these samples because they are far from the samples with which the system was trained. So overfitting should always be reduced as much as possible, but I have to say anyway that overfitting can happen in practice not only because of this, but just because the images are acquired in different hospitals under different conditions, for example, with different illumination. So in that case, we could even have some sort of overfitting, but okay, it should be reduced, that's for sure. And the other interesting challenge worth mentioning here is explainability. Explainability is about just trying to explain why the artificial intelligence system took a decision, okay? If we talk about a human being, you can ask why you took a decision, but what happens with an AI system? As you can imagine, this is a very crucial issue in a field like medicine. And before we saw that deep learning systems are very good in terms of performance. However, I have to say that they are very bad in terms of explainability. That's why they are known in this respect as black boxes. Actually, in practice, there seems to be some sort of trade-off before performance and explainability, because if you want to have an explainable system, you can use a more conventional machine learning approach, which is explainable, it's easy to know what's happening. But if you want to have a high performance, maybe you have to move to a deep learning approach, which is not explainable at all. So this is the trade-off which usually exists in practice. Okay, now let's start with the second part of the presentation. I said before that I would focus on some more specific problems which we have faced in our research work. I'm part of the medical image analysis group in the University of La Laguna. We are not really, in the last year, we have not been really so much interested in the diabetic retinopathy, but on another type of disease, very important as well, which is glaucoma. Glaucoma is one of the main causes of blindness in the world. It is known as silent blindness because it's characterized in many cases by the almost absence of symptoms. That makes this disease very difficult to diagnose, even by specialists in the field. And this is also due to the lack of clear biomarkers in the image, for example. If you remember, we saw before example of an image in which showed some spots. It was about diabetic retinopathy. So we could see at least some spots like hints of what's happening there. In the case of glaucoma, in its early stages, that's not so clear, and that makes the problem really challenging. So we have a challenging problem. So in that case, how can AI help? Well, before leaving this slide, just let me tell you something about this picture here. As you see, this is a cropped version of the image I showed before, because in the case of glaucoma, the most useful information is usually focused on the optic nerve head, and that's why the image has been cropped around the optic nerve head. And here we can distinguish some interesting structures, like the optic disc here, the optic cap, which is this region like more white here, and the retinal ring, which is the region in between, okay? So how can we face this problem? There are, in deep learning, there are two main types of deep learning architectures. Of course, I have no time here to explain this in detail. So I just try to give a very quick overview about how this works. We have convolutional neural networks. Here we have a schematic picture. So we have at the input of these systems, we have an image, and at the output, what we have is a probability, is the probability assigned to the different classes or categories considering this problem. For example, we would like to classify different types of robots, for example. So in this case, we would have here some outputs corresponding to these different types of robots, and we would get a probability of this specific input to be one of them. What we have in the middle, what we have are a lot of layers of artificial neurons. They are organized in a hierarchical way, so that when you take a lot of images to train these systems, what you do is to try to adjust the parameters of these neurons, which are called weights, so that if you train it correctly, so you train your system correctly, what you have in the end are some so-called feature maps, because you have here features that hopefully, if you train correctly, they will be good features to try to, as I said, to classify, in this case, the different types of robots. That's more or less how convolutional neural networks, and just before leaving this slide, just to say that the word convolutional is related to the basic operation which is performed at the level of the, of these feature maps, which is a convolution, is a very known operation in the field of computer vision, okay? The other type of architecture for deep learning used nowadays is the transformer architecture. Transformer architecture is much more recent than convolutional neural networks. It started in 2017 approximately, and since then it has become de facto a standard for natural language processing tasks. Because before that, what it was used for this type of task was recurrent neural convolutional neural networks. But when transformers appear, they performed much better. So that's why they have become the standard of the art in that respect. And for example, they are used in systems like ChatGPT, for example, and similar. We have nowadays. I'm sure you've heard of them, as everyone. Well, of course, I have no time here to explain how a transformer works. Just to say that in this case, instead of using convolutions, they are more focused. They are more. They use some sort of self-attention mechanism, okay, to being trained. Okay, but I'm saying that these transformers are used for natural language processing. That means that they use words as inputs, but we are interested in images. So how can we use transformers with images? The response to that question is the answer to that question appeared in 2021 in a very famous paper entitled "An Image is Worth 16 by 16 Words, Transformer for Image Recognition at Scale." Well, the authors of this paper did a very simple thing, really, but very effective. They just took an image, as you see here in an example, and they split the image into different patches, as you see here, and that was the input to the system, to the transformer, so that these patches were treated as if they were words. And in that way, this could be also used for classifying images. Okay, there's a strong debate in the deep learning community about which is better, vision transformers or convolutional neural networks. To try to answer this question in our field, we carried out some experiments which were published in a publication, which is here is shown the DOI if you want to have a look. And what we found is shown on the slide. Okay, we have here a table, and we use different test sets. These ones you see here. And in the first, okay, I have to say also that we use different architectures for convolutional neural networks and also for vision transformers. So what we got in all the tests with all the test sets in the first position was, as you see, a convolutional neural network. In the second position, we can find some transformers here. These are transformers, but anyway, I have to say that the difference, as you see, is very little. So I would say that in general, they perform very similarly. Actually, what is expected is that maybe if we train the transformers with a very big training set, maybe the transformer could perform better than CNNs. But in practice, in medicine, you usually have hundreds or thousands of samples to train your systems, because it's not easy to collect samples in the medical field. So I think at least according to our experience, they will perform very similarly. Okay, now let's move to another example, because so far we've been talking about predictive AI. Okay, we've been talking about to predict if a input sample is a glaucoma or is a normal image, a healthy image. But how about generative AI? Generative AI can also be used here. Is commonly used as a way to generate artificial samples, artificial images. We can make your training set bigger, because as I said, the more images you have, the better the training you will get. Yeah. But in our case, we use it in a different way. We use it for predicting glaucoma progression. So this is more about prognosis. You have a scheme of the type of system we use. It was a very popular generative adversarial network. And here maybe this is clear for you. What we have on the left here, this column is the progression of the disease for some specific subjects. You see here we have of course I'm showing a different type of image. These are not eye fundus image, as you see. It's a ganglion cell map image. So here we have how the image progress, okay? How the glaucoma evolved with time. And what we have, but this is the real one, okay? This is the real image showing the progression. And what we have on the right is the image generated by our system. And as you see, they look, at least visually, they look very similar. Anyway, we wanted to be sure, we wanted to check how similar they were, and we carried out some experiments with our experts in the field. So what we did is very simple. We just mixed in one set real images and fake images, okay? The real ones and the ones generated by our artificial intelligence system, and we asked the specialists to classify them in real and fake. And this is the accuracy we got from them. It's a 57%, which is a very bad accuracy, very low accuracy, very close to random selection. So that means that the neural network is doing a good job, because even the specialist is not able to separate the real ones from the fake ones. So the images we obtain are very realistic. Okay, now let's change a little bit again, and let's move to something else we discussed before. If you remember, we talked about explainability, and this is a very hot topic research topic in the last years because of this deep learning systems, as I mentioned. And what we have here is an example of a research we carried out, which was also published in a journal. Here you have the DOI if you want to have a look. And this is actually showing the most popular explainability method in practice. It's a visual method, as you see, and it's called saliency or attribution maps. Essentially, what you see here is some sort of heat map showing where the warmest areas correspond, or it is expected to correspond to the parts of the image which are of the input image which are more relevant in the decision taking by the AI system. So here you have different examples with different techniques. This is what you get. And well, our conclusion in our research was similar to the conclusion reached by other researchers. And the thing here is that, you know, if you show this to the specialists, it's really not that useful, because even if you have a visual output, what does this really mean? You only have some spots there, but you don't really know what's happening behind that. And even it may lead to wrong conclusions or wrong impressions of what's really happening if you try to justify somehow why this has this appearance. So in general, I would say that this is not very good for the medical field. Maybe it's good for another type of problems, not so critical, but not for the medical field. So I will propose a different way to do this, to do this explainability issue. So this is using an interpretable surrogate model to mimic the probability outputs of a deep learning model. Here we have a scheme of how this works. We also publish this in a journal. Here you have the DOI if you want to have a look again. And okay, we have some input images that we can use to train a neural network, for example, a convolutional neural network. And what we get is a black box model, as we know. We can at least try to explain that with a saliency map, but we saw that this does not provide very good results. Let's try a different way to do this. What we did is to extract some features from the input images used in the training. These features had to do mostly with morphological features extracted from the geometry of the disc and the cap. You remember we saw before the disc and the cap areas. So we extracted some geometrical features which are of interest to the specialists. Of course, we need their support in this. And with these features, we can train a more traditional machine learning model, intrinsically explainable, for example, the decision tree. And we can obtain a decision tree which can provide some sort of explanation. It's much more easy to understand what's happening. So the question which arises here is, were we really able? Okay, I forgot to say one important thing is that this decision tree was trained in a regression mode, so that the idea was that to try to reproduce, to mimic the probability outputs we got here, okay? So the idea was using these features to try to obtain the same probability outputs here than here. So as I was saying, the question arises, did we manage to do that? Well, I have to say that no, we did not get it. This is shown here. This graph here shows what happened. R square is a way to measure the similarity, the degree of similarity between the outputs of the deep learning model of the decision tree. And as you see, we got a very low R2 value for the decision tree we trained, okay? So that means that it didn't work. However, you see on the left of that, we have another example that seemed to work much better. And that's because we train our deep learning system with a different type of image. And that's here you have an example on the right of this type of image. What we did was to simplify a lot the image, the original color images, just by retaining, as you see here, the outline of the disc, optic disc, and the outline of the optic cap, and to put that on an homogeneous background. Okay, and we train our deep learning system with these images, and as you see, we were able to reproduce, in this case, the probability outputs with an explainable system, with a decision tree. Well, this is logical because in this case, the neural network has no chance to learn features other than geometrical features, because that's the only information contained in this type of images, as opposed to what happens when you use color images. In this case, it seems that the neural network is not really relying on this type of geometrical features, but using other types of features that we don't know. So, well, in this case, it only worked by training the network in this way. And finally, the last example I'm going to show has to do with something called deep metric learning. This is something we are currently doing in our research group, and we are trying this as an alternative to the usual way to train a deep learning system, because as I said before, what you usually try to reach at the output of our network is an estimation of the probabilities assigned to the different classes or categories. In this case, this is different. What we try to do explicitly is to try to obtain a feature representation of the samples, so that the samples belonging to the same class are clustered together, and they are kept well separated from the other clusters corresponding to other classes, okay? That can be done using different types of deep metric learning formulations. But in any case, I think that the most important thing here is that this way to approach the problem can be better, not only maybe in terms of performance, but also in terms of explainability. I will tell you why. Okay, I think it will be clearer in using this example. On the right of the slide, you have an example of how these samples were clustered by training the network in this way. You see here the cluster corresponding to the glaucoma samples. You see that here we have a low variance, which is good. And in the case of the healthy samples here, okay, they are somehow also clustered, but they have a much higher variance. Let's now have a look at the left side on the slide, where we have here we have a query or a test sample, and the idea is how to classify this. What we do is as you see below, is to choose the closest 6 neighbors to this test sample. That means the closest samples according to the distance measured using the specific metric formulation which was used during the training. So, okay, if you show this to the specialists, the idea here is, okay, we classify this query sample because, as you see, the other images in the training set, this is very important, these images are in the training set, the closest ones are all normal. So if all of them are normal, it's logical to think that this query or test sample should be classified as normal as well, because it's more similar to the normal samples than to the glaucoma samples. And I think this is, for the specialist, is like some sort of intuitive way of explaining things, because he already knows about these training samples. This makes sense for him. Maybe he previously diagnosed these samples. So what we are saying here is, okay, this new sample will be classified as normal because it's similar to something you already know. You have already some previous experience with it. So I think this is intuitive, and maybe some way of explaining things to the specialist. We have to check this anyway, because we are, as I said, this is a research in progress, but hopefully this will be good for him or for her. And just before leaving this slide, just let me mention that, as you see here, we can also measure these distances, and this can be useful also from a robustness point of view, in the sense that maybe if these distances are very big, it could happen that this test sample could be considered as some sort of outlier in the problem, because it seems that what the network has learned is far from what this test sample represents. So in that case, I think it would be maybe more safe to just discard it and try to retrain your system. Okay, I'm finishing. Just but last but not the least, I did not want to skip this, because I think it's interesting, because these retinal images we've seen so far contain information which can be used not only for diagnosing eye diseases, but also for diagnosing other types of diseases. And in the last years, there have been some approaches to this. For example, if this image is extracted from a publication, in here you have the DOI, if you want to have a look at it. And as you see, we are talking about something different, about Alzheimer's. However, being a different disease, you can find on the images of the retina some hints about this disease. For example, here you have the increased excavation of the optic nerve, or the increased cap in the optic nerve. So these are anatomical manifestations that can be useful for the diagnosis of Alzheimer's in this case, but it can be applied also to other type of diseases. And okay, just to finish, I don't want to forget to mention that okay, we are within STARS U, so very related to this talk. We are currently preparing a proposal for an action in the program, in the research program Horizon Europe, about explainable and robust AI applied to medicine. So it has a lot to do with what I've been talking about. And in this action, there will be 4 members from STARS U, University of La Laguna, Braganza, Franche-Comté, and Krakow University of Technology. So we are working on this, and hopefully we will get funded, but it's a very hard call, so we will see. Okay, thank you very much for your attention.
Thank you very much, José Sigut. It's very interesting. There's a lot of food for thoughts, and I'll hope that there will be some questions or remarks from participants as well. So we open up the floor for if there are any questions or remarks to José on his presentation. I can't see any reaction. So I'll start up, Jose, because I think it was most fascinating and interesting, and I'll understand directly that the needs here are immense, as you have explained about the possibilities of using this. Is just one application of possibilities, and there's several others, of course. But so when you magnify and think about the possibilities, where you see that this is something that will take quite a lot of attention in many areas, and the application as well. But I would like to start up with considering your knowledge and the research you're doing together with colleagues. What would you see as the largest challenge for introducing the technology and the way of thinking and doing this? Is this the experts, the doctors, and their reliability on the system, or do you think that humans are afraid of when they hear how the images of them are being used and so on? So what do you think about the challenges for the introduction in this context?
Well, I actually mentioned two of them, but you know, I would say that maybe the medical field is one of the most difficult ones to introduce this type of technologies. Anyway, as you saw in the timeline, on that slide, there exists even some systems we have been approved by the FDA, for example. So that's really very remarkable, because if it was approved by FDA, it means that you can use it in the real clinical practice. But it's true that there are many challenges which have to be faced, because you have to try to to make the specialists be trust on this technology, and to get that, you have to face, for example, as I said, the problem of overfitting and systems which are not really ready, prepared for dealing with any sort of image you can give to them, for example. And another strong challenge, of course, is explainability. Okay, imagine instead of using AI as we use another specialist, another expert. Okay, you have to diagnose cancer or whatever, or some of these eye diseases, and you can, if this expert, human expert, takes a decision, you can ask him or her, why did you take the decision? And he or she can explain in natural language what he or she thinks is happening there and why he took or she took the decision. In the case of AI, this is a real challenge. It's a topic of research nowadays, because it's not that easy at all. And the problem is that, okay, we've managed to get systems like this deep learning system, which are very, very good. You've seen many times, okay, deep artificial intelligence is doing better, is performing better than humans. Oh, fine, it's true. It's true. But in the end, if you have no way to explain what's happening there, can you really trust on that? Okay, even if you have a 99% of performance accuracy, oh, excellent in practice. But in a real scenario, you have a specific subject you have to diagnose. Your system will be never 100% perfect. So you have to solve the problem for that specific subject. So you cannot trust the system just because it has a very, in general terms, it has a very high accuracy. So you need explanations. So that's, I think that will take still some time, because it's a hot topic and it's not easy, because these systems are, as I said, like black boxes, and it's not easy to find out what's happening there. I've been working on that on the last years, and it's a it's a hard issue.
I can understand that it's very much about that you're as an expert, you are reduced to look upon and make the judgment, but also the acceptance of what the AI system has done for you. But then again, the number of tests, the number of possibilities, the possibilities of that you actually screening a large population, that you because you could do so much more than you can't never have so many experts that will do the similar thing.
Yeah, you're right. Actually, in a screening, that's a different scenario. Maybe these systems, as they work nowadays, they are more more suitable applied to screening, because screening is not so critical. Screening, the main objective is to try to identify subjects let's say at an early stage, so that they will be treated later, maybe in a hospital. For example, I saw this Retinal program we have in the Canary Islands. That's very good, because in a primary health center, doctors who are not really specialists in this subject, but they of course they have some general knowledge, but at least they are able, with the aid of this artificial intelligence, they can distinguish, okay, this is clearly healthy, but this should be analyzed in more detail. So okay, these ones should go to the hospital, but not all of them. That's, as you said, that's a very good, because you have the way to filter out somehow the patients from the beginning at an early stage, and that means in practice a saving of money, a saving of resources. So from that point of view, of course, artificial intelligence can help a lot, and it's not so critical, the decision there, I would say.
Yeah, and what you have talked about are of course one application, one area. When you look upon the tried as an researcher in informatics, information systems, the wider areas of actually introducing this into other fields and make it more general in other areas as well, which kind of obstacles or issues to address do you see will be with the major ones? Will it be the technology? Will it be that the acceptance of and or will it be which kind of problems or obstacles do you see when we switch into other medical or other issues when using these kind of models on the black box, on the AI in general?
Well, there are many of them. We have to take into account that as everybody knows, the doctors in a hospital, for example, they are very busy, and if you try to introduce this sort of technology in their daily routine, it has to be something very, very optimized and very it has to be in accordance with what they usually do. Because sometimes it happens that, from the point of view of the people working in machine learning and these things, oh, you are so happy because you you found very good results and everything looks very nice. But when you show that to the specialist, says, okay, but this is not in this way is not so useful for me, because it's not something it can really be easily adapted in a real scenario with all the constraints you have there. And well, it depends, of course, also on the type of problem you work with. In this case, we are talking about a computation resource, but in some cases that would mean introducing some sort of new technology that could, for example, introduce some, for example, imagine some interferences in the system. If you want to take your invention to operating a scenario in a hospital. So there are a lot of things that can, depending on the problem at hand, there are a lot of things that can be an obstacle there for really doing that. Actually, there are a lot of papers which deal with this subject, just because it's nice to have so many people in the machine learning community working on this, but guys, consider that this should be translated to the real world. So you have to, the human factor there is crucial. In the end, you have humans working there, and you cannot put something there which is like very intrusive, you know, in the system, and does not fit well. So yeah, it's a very serious and very important problem, and the definite problem you have to solve if you want really to start really working in real scenarios as daily practice. Yeah.
Yeah, thank you very much, Jose, for those I think very important, and that you have a lot of insight and understanding, and where the problems actually might be, because we are humans and we need to adopt the technology and accept the technology and use the technology, and how we could see to do that, and not just be opposing and against, and see the possibilities and use it in the best possible way. So yes, thank you very much for this talk today, Jose, and we'll continue with the STARS talk. We're beginning in September again, and there will be a series of talks during the autumn, and it will all be advertised on the web page and through the different channels for the STARS EU Alliance. So thank you very much, Jose, and thank you for all the efforts made behind this, and it's really interesting research you're doing here.
Thank you all. Bye bye.
Thank you.
Thank you.